let's flow. So you understand that his was not really the first, okay, but his theory was somewhat different, um, because he was more specific about the things that he discovered. Uh, Give me a minute, please. I don't know why this thing came up. Okay, hope you can see my screen now.
Yeah.
Okay, all right, okay, all right. So every theory has what you might call the the postulates or the things that make up the theory, right? And let's look at the first one. All right. Now, did you in class? Did you guys look at the Dalton's atomic theory? Did you guys look at that?
Yes.
Okay. All right. So I just want to make sure that these are the theories, the postulates that you guys covered. The first one is that every bit of matter is composed of tiny uh, particles called atoms. Okay, so if we
Mm-hmm.
understand that, it's trying to say that atoms are the smallest um, particles you can get in any piece of matter. And then that leads us to postulate two, that an atom is indivisible. That means you can't break it down further than uh, what it is. Okay, so that's the second postulate. Um, the third one says that atoms can neither be created nor destroyed. Okay, they come that way. And then the fourth one is that atoms of an element are identical in shape, in size, in mass, and in other properties, which we'll see later, both chemical and physical properties. And then atoms of different elements are different in their properties. Now, we would also see that some different elements are somehow have similar, uh, we like called properties. Okay, yes, similar properties. And then atoms combine with each other in small holes. And then um, all chemical reactions are due to a combination or separation of atoms. Now, let me ask, how many um, how many postulates did you guys talk about in class?
Pardon?
How many of these did you guys cover in class? How many of these in the atomic theory did you guys cover in class?
Um, I'm not really sure.
Okay. But you said you people talked about the Dalton's atomic theory, right?
Yeah.
Okay. 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 All right. So let's see. Let me go to where we have the model for Dalton Dalton's atomic model. I think this should be this one. Okay. Just hold on. Let me open it. All right. Okay, you can still see my screen, right?
Yeah.
Okay. All right. So I'm going to Dalton's atomic theory. So, well, this is still a reminder of his theory, but let's look at his model.
Like it. 3%. What is this thing?
Okay.
It's charging him.
Come from the scenery, bro. You're moving like I'm not gonna play after, just move.
So,
All right. That one was not too
sorry, can you
detailed.
please?
I think. Sorry, did you say something?
No.
Okay.
Hello.
Okay. Can you hear me now?
Yes.
All right. Okay.
Hello.
Okay. Hold on a bit. Let me go back to sharing my screen. Okay. Can you see my screen?
Yes.
Okay. Okay. So these are uh, still the same postulate, but this is summary of his theory, right? Dalton believes that there was nothing smaller than an atom, right? So this is
Mm.
his model. Now take a look at this and see if it uh, aligns with what if it's similar to what you learned in class.
Mm-hmm.
Okay, so this is his theory. Okay, so the main things about his theory are that we don't have that atoms are the smallest particles, right? So that means that he was not the one that who came up with um um the fact that there could be neutrons, electrons, and protons, all right, inside an atom. But well, at least he tried. He came up with something that was close to what we would say we actually make use of today. So, do you think this is something you can remember if you are asked?
No, no.
You don't think so? Take a look at it closely. I think this is a summary of what this theory is. The first is that all elements are composed of atoms. Atoms are indivisible and indestructible, and atoms of the same element are exactly alike, right? Atoms of different elements are totally different too. And then compounds are formed by joining of atoms of two or more elements. Okay, so this is a summary of it. Okay, okay. But then let's see. Maybe by the time we look at the other model, we will be able to compare the next one with Dalton's own. Okay, so let me take a look at what you have after Dalton's atomic model. Okay, so I see there in the topic that you wanted us to discuss, chemical properties. What chemical properties are those? Is it in terms of related to his atomic model or chemical properties in general?
I think chemical properties in general.
Okay, and you want to give me an example so I have a hint of what you are talking about. Um, chemical properties of elements, right?
Yeah, g- yeah, of elements.
Okay, okay. All right. Just give me a minute. Let me, because I don't want us to go off course while when in our studies. Um, chemical elements, chemical properties. Sorry. Um, okay. Okay. All right. So I have two slides here. Let me see. I'll open two of them side by side. Um, Now there's chemical properties, and then there's chemical properties of matter. Um, okay, don't worry. If you see it, I'm sure you'll be able to identify which one it is that you guys did in class. Okay, so um, let me share my screen now so that you'll be able to tell which one it is. Okay, so confirm that you can see my screen. Can you see my screen, Mason? Hello, Mason. Can you see my screen?
Yeah.
Okay. All right. Okay. So um, take a look at this slide on chemical properties. Um, does this look like what you guys did? I don't want to go out of the scope of what you guys covered in class.
I'm not sure. I can't really remember because I don't have my book on me.
Okay. Uh, when are you guys taking this test?
On the 28th.
Okay, that's Wednesday.
Yeah.
Okay. Okay. Um, is it possible that when you get to school tomorrow, right,
Mm-hmm.
um, you'll be able to either take a picture or do screenshots of your notes in class
Okay.
so that we can take a look at the exact things by the time we meet for class tomorrow.
Okay.
Yeah. So that um will not uh review something uh, different from what you did, and that would be kind of confusing. I wouldn't like that to happen. Okay. Okay. But I know that there was a time that we talked about chemical changes and all that. Um, that uh, chemical changes, chemical properties. When we talked about an iron rusting, okay, so it changes it, and that chemical change cannot be reversed. Okay, so anyway, let's just leave that bit. Let me see. Um, Mendeleev's
Wait,
table. Yes.
can we just do the the Dalton's at Mendeleev table.
Okay.
Dalton's
Okay.
atomic
Okay.
model and Mendeleev's, and then I'll try get the thing for tomorrow, the chemical properties,
All right.
physical trends, and chemical trends.
All right. Okay. Okay. Sure thing. I'll do that. Let me get uh let me get lines of Mendeleev's table. Okay. Okay. So basically, Mendeleev's table is what we have come to accept as um periodic table. All right. So I know there was a time that we had to memorize the first 20 elements. Did they tell you guys to memorize anything in your own case?
I'm not sure, but I probably need to memorize it.
Okay. 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 I need to um 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 okay, it's clear. It's looking clear. Okay. Okay. Let me share my screen so you see if it looks familiar. I'm sure it's going to look familiar because there's only one. Okay. So can you see my screen now?
Mm-hmm.
Okay, so his the Mendeleev table, which is we would also call the periodic table, right, is based on two facts: the atomic mass and the similarity of chemical properties. So you notice that all the ones that have similar chemical properties were grouped in one group. So if you look at group one elements, all of them have um, similar properties. They are all metals, okay? And yeah, that's the group one element. So Mendeleev understood that atoms are not really the smallest elements, like Dalton said. He said that he's of the view that we have um, protons and neutrons, which make up the atomic mass. Okay, and then electrons are around, in the shells around the nucleus, where you can find the neutrons and protons. Okay, I hope what I just
Mm-hmm.
said now sounds familiar. You understood what I said, right?
No, not really.
Okay, well, why did you guys learn about the nucleus in an atom?
Yeah,
Okay,
I
and
think
what is inside the nucleus? The neutrons
the
and
protons.
protons. About that.
Yeah,
Okay, all right. So, how about the term atomic mass? Do you are familiar with the term atomic mass?
yeah.
Okay, so the atomic mass is simply the sum of the protons, the number of protons and neutrons in an element. Okay,
Okay.
while atomic number is only the number of protons. Okay, take note. Not We don't have any business with the electrons that are spinning around. Again, I'll say it. The atomic mass is the sum of the number of protons and neutrons, while the atomic number is simply the number of protons. So you can just think about it that the mass is usually more than the atomic number. Atomic mass is more than atomic number. Okay. So if you look at this slide I'm on right now, that's before if you consider, which one should we consider? Um, okay, let's take a look at sodium. Or okay, no, let's take a look at fluorine. Okay, anyone will do really. Anyone will do. If you look at fluorine, its atomic mass is 19.00. Okay, so that's the atomic mass. That is the mass of the proton and neutron. While the atomic number is 9. Okay, that's the number of protons alone. It's 9. Okay, so um that was what Mendeleev's table was built around: the atomic mass and then the similarity of chemical properties. But now, the thing about chemical properties, let me give you an example, right? What would you say is one outstanding chemical property for metal? What would you say is one
Um,
outstanding chemical property for metal that you know?
is it? It's a good conductor of heat and electricity.
Good, 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 good. Okay. So you will notice that all of them have that characteristic, which you just mentioned. So so basically, all of them should be what in one in well in a particular
In
group.
one group.
Okay, it depending on, yes, depending on uh uh the similarity, okay, of their chemical properties. Now, does it now mean that you may not find some other element may conduct electricity. You may still find, but metals do it exceptionally well. They do it
Mm.
better than others. Okay, so
Okay.
that's why metals are usually used as conductors, and while non-metals, insulators, are made of non-metal. Okay, because they don't um, um, conduct electricity as well as uh, uh, metals. Okay, all right. So let me see if we have any. I don't know. Is this clear enough? Okay. Okay. Can you see the oh, this is not the right one. Let's let's go for the right one. Mendeleev. Periodic table. Okay. I think this is it. Yeah. So I want one that would help us to see the trends. Periodic table development and trends. Okay. Can you see my screen?
Yeah.
All right. So like I said, usually we in our own time we have to memorize the first 20. If you are going to memorize the first 20, you would need to know either a song or an acronym. And that acronym may well sound like telling a story. So I don't know if you've made any attempt to um if you have any way you devised to memorize it, do you?
Pardon?
I mean, do you have you developed any method for memorizing the elements of the, not all of them, of course, maybe the first 10 or first 20 elements of the periodic table? Have you gotten any means of that
No.
doing that?
No.
No. Okay, so what I usually do is I encourage you to get the best, something that works for you. But then let's move away from memorizing it, right? Let's understand the trends, because that's a very important part of it. Okay, the trends. All right, what we call the trends. I think that was part of you uh, what you highlighted, the physical trends and chemical trends. Okay,
Okay.
all right. So here we go. Okay, all right. So let's look at the trends now. There are quite a lot of things here, but I'm not sure we'll be able to go through all of them. Let's just focus on uh, what needs to be focused on. Let me go for the thing. Do my best to. Uh, okay, so this is what I was talking about. The non-metals are, are elements that are poor conductors of electricity and heat, and generally gas and solid. Um, let's see. Okay. Um, yeah, okay. Hmm. Um, friends, friends, friends. Okay. So which of the groups did you guys talk about? You guys talked about metals, right?
Yes, I think so.
Okay. So for instance, let's look at group one, the elements in group one, and then we'll talk about electronic configuration, right? And the periodic table. So if we look at the elements in group one, um, uh, let me see. Did you guys talk about the 281 um, um, configuration? 281, something like that. The one that has two electrons in the first shell and 8 in the second shell, so on and so forth, stuff like that. Did you guys talk about that?
No, wait, what is it?
Hold on, let me see. I want to go to where the periodic table is. Okay, you can see the periodic table, right?
Yeah.
Okay. Now I want you to take a look at these guys. All the elements in group 1A. Okay, the one I'm highlighting with the red annotation. Excuse me. So all of them have one electron in their outermost shell. So for instance, lithium would look something like this. The nucleus
Mm.
will be at the center. The nucleus will be at the center. And then around that nucleus, you have electrons going around like as if they're elements in the orbit. Okay, so they're going around it. So lithium will have two electrons in the, let me draw this. So this, what I'm drawing now is one electron. And then what the next one that I'm drawing now is the second electron. These two electrons are going round that orbit. Okay, they're going round that orbit in the outermost shell. Okay, so this would be for I want to do for lithium, and lithium has three, right, as its atomic number. That means it has three electrons too um, in its outermost shell. So right now I've drawn only two. Okay, so to draw
Mm.
the completion for means I'll have to draw another shell around the inner one, and then this will now be my third electron. So what does that mean? According to Mendeleev's the way Mendeleev model looks, the first shell can only take two electrons, okay, while the next shell after it should be able to take 8 maximum. But in this case, lithium only has 3. So we'll have 2 in the inner shell and 1 in the outermost shell. Okay. Did you guys do something like this in class?
Wait, can you please repeat that?
Okay. Okay. So I said this is how lithium, I'm just using lithium as an example. Okay. Lithium's electronic configuration look. The inner shell contains 2 electrons, while the shell after around that inner shell contains 1 electron. And I said, how do we know that it is so? Because lithium's atomic number is 3. Okay, so that means there are 3 electrons altogether in lithium. Okay, did you get that?
Mm. Yeah.
Okay, so now the question is this: if lithium wants to react with another element, will all 3 of its elements react, or only the one in the outermost shell? Which one do you think would would it would react?
Is it the outer shell?
Yes, exactly. It's the outer shell. So the outer shell, because of its closeness of proximity to the other element that lithium may want to react with, the ones in the outer shell would, you know, be free to react. And that's what happens in chemical reactions. So this is just an example, using lithium as an example. All the other elements have their own um, electronic configuration. Okay, so I'm trying to go to the part of this slide that has the trends. Let me see if I can find it and then quickly come back to here. Okay, I think this is it. Okay, periodic trends. All right. Okay, here we go. You can still see my screen, right?
Noah? Mm-hmm.
Okay, good. All right. So periodic trends are specific patterns that are present in the periodic table that illustrate different aspects of a certain element, including its size and its electronic properties. All right, so let's take a look at this. The trend for atomic size. Okay, so for atomic size, um, so nobody is going to ask you to define it. Okay, it's just for you to understand that the atomic size usually is an indicator of the size of the atom. Okay, the size of the atom. So down a group, how does it play? Down a group, it increases as you move down a group. Did you get that?
The atomic size.
Yes, the atomic size. It's a trend.
Mm.
It increases as you move down a group.
Okay.
All right. Now
Uh,
you can understand that based on what I just illustrated here. Lithium. Okay. If you want to do the electronic configuration for the element under lithium, you will see that it will not just have two shells like lithium. It will have three shells. Do you understand what I'm saying?
mm.
So based on that, the more the number of shells, the bigger the atomic size. Okay, so let's look at the other trends that relate to atomic size, right? Atomic size decreases as you move from left to right across a period, and you will see the reason and the effect of that decrease. Of course, moving from left to right is also an increase in the protons, causing greater attraction to electrons. Now, you see this last point. I want to explain it carefully to you. Now, I want you to notice something. Do you agree with me that um just like north and south pole in your magnets attract, that is unlike poles, right?
Pardon? Pardon?
In in a magnet, when you're working with a
Mm-hmm.
magnet, right,
Mm-hmm.
the north south pole they attract, isn't it?
Yeah.
Good. In the same manner, positive protons, that's positively charged protons, and negatively charged electrons also will do what? Attract each other. Do you agree with that?
Yes.
Good. Now, you know that thing that you when you're dealing with a magnet, the closer the magnet gets to another magnet that it can attract, the stronger the magnetic pull. Do you agree with that?
Yeah.
Okay. So what does that tell you? The same thing here. If atomic size is a measure of the size of the atom, if the what do you call it? atomic number is increasing as you go from left to right in a periodic table. The atomic number is increasing, which means the number of electrons is increasing. And not just that, the atoms are shrinking in size. What does that tell you? It means that the electrons in the outermost shell are closer to the nucleus. Don't you can you see that fact? Okay. Did you understand what I just said?
No, no, not really.
Not really. Okay, don't worry. But then you you this trend about atomic size increasing as you move down a group. You understand it, right?
Mm-hmm.
Okay. Okay. I'm trying to see how best I can explain it. Okay. Anyway, can you see this drawing, the sketch I made here for lithium, the lithium atom?
Pardon?
Can you see this sketch I made here? The one I did on the right hand side here.
Yeah.
Okay, good. Now, I in the nucleus, which is in the center, inside the nucleus, okay, you have positively charged protons, right?
Uh,
Okay. Now, those positively charged protons are exerting an attractive force on the electrons around the nucleus, right?
mm-hmm.
Good. Now, I want you to see that if you see that arrow that I drew now, the distance between the nucleus and the outermost electron, if that distance is reduced, I want you to listen. If it's
Mm.
reduced because atomic size shrinks or reduces, then it means that the protons, the nucleus, will have a stronger pull on the electrons in the outermost shell. Why? It's just like that magnet. The closer the pin or the thing it's trying to attract itself to is to it, the stronger the magnetic pull. Did you get that now?
Mm-hmm.
Okay, that's good. All right, so that's just what I wanted to say. So when we want to explain certain trends, it should not be, you know, like confusing. Okay, so let's move on to the next trend. Okay, but let me ask, do you understand the trend for atomic size?
Pardon?
And do you understand the effect of the trend for the atomic size?
Yeah.
Okay, all right. Um, okay, so this is a diagram. I'm sure you can still see my screen, I hope. This is a diagram that shows the the um, the trend for the atomic size. If you look at it carefully, right, atomic size increases from top to bottom. Let me annotate where where I'm talking about. From top to bottom, you can see the atomic size is increasing. But when you are going from left to right, that is from here to this direction, you can see the atomic size is getting smaller and smaller and smaller. Do you agree with that?
Mm-hmm.
Can you see that? Okay,
Yeah.
okay, that's good. All right, so let's go to the next. second. Which is, okay, did you guys discuss anything like ionization energy?
I don't think so.
Okay. The energy required to remove an electron from an atom. Energy required to remove an electron from an atom. Okay. All right. So, I don't think you guys discussed this shading effect. I don't think. Okay. All right. Now, if the ionization energy means the energy that's required to remove an electron from an atom, do you agree that the stronger the pull of the nucleus on the outermost electron, the harder it will be for us to remove the electron from that atom? Do you agree
Yeah.
with that? Okay. So remember, as we go from left to right, atomic size does what? Reduces.
It
So
reduces.
that, yes, so that means nucleus will have a stronger pull on what? The outermost electron. So that means it will be harder to do what? Remove an electron from the atom as you go from left to right. Did you get that?
Yeah.
Okay. So that's what we should expect. The ionization energy will increase. Okay. So ionization energy, um, you can even see it there. Look at the third point. Ionization energy tends to increase from left to right across a period. It increases. Okay. But where does it decrease? It decreases as you go down a group. Why does it decrease? The reason is very simple. Atomic size, instead of reducing, increases. So if atomic size is increasing, guess what? The distance between the outermost shell and the nucleus is also what? Increasing. And if you keep increasing that distance, what will happen? The pull of the attractive pull from the nucleus to the electron will be smaller. Why? Because the distance is increasing. Okay. Okay. Did you get that?
Yeah.
Okay. Now, I don't, like I said, I don't want to push it too far. Okay. I don't want to push it too far so that we don't go outside the scope of what you guys did in class. So I'll just really depend on the notes you'll be able to get for us tomorrow so that we can, be, very spot on when it comes to what we are learning um, or reviewing for your test. Okay, so the next point here is
No.
negativity. Can you hear me?
Yeah.
Yes, sir.
Yes, sir.
Okay, all right. So, electronegativity is the ability of an atom to attract electrons to itself. Typically, electronegativity is something that non-metals specialize in. They usually like to attract electrons to themselves. Now, um, I mean, you understand why that is possible. The nucleus contains what? Protons. So if the pull from the nucleus is strong and there are electrons from another element close to that nucleus that the pull is strong, it will want to pull electrons from that other element or that other atom. Okay, so in this case, we're just looking at should I say non-metals. So the trend in this case is what? Electronegativity will do what? Decrease from top to bottom. Why? Because the atomic size is what? Increasing. Remember, electronegativity is the ability of an atom to attract electrons to itself. So if the size of the atom keeps growing bigger from top to bottom, then that means electronegativity is decreased because the distance between the nucleus and the outermost electron is increasing. Okay?
Hmm.
All right. Okay. So let me see if the physical terms that we talked about. Okay, the zinc. Okay. All right. Did you guys talk about electron affinity?
I'm not sure. I don't think so.
Okay, all right. So skip that. All right. How about metallic property?
I think so.
Okay. So you know this one, right? Within a period of the periodic table, the elements become more non-metallic from where? Left to right. As you go from the left to the right. Okay.
Mm-hmm.
Okay. And then of course, from top to bottom, we would expect metallic properties to increase. Okay. Okay, so this is more like a what do you call it? A chart that will help you to remember um, all those things. Okay. But then let me see what you guys took down in class so that you have a more detailed stuff to work with tomorrow. Okay, so um let me quickly take a look at what you think. Physical trends and chemical trends. Okay. Okay, so it looks like some of these trends I discussed now, I'm not sure. Are they chemical trends? Are they physical trends? Some of them are chemical in nature, but we're talking about um, um, chemical properties. Okay, let me quickly see if we have any slides here for chemical reaction. Hmm. Mm, mm, that's not right. Okay, let me see. Let me just search for chemical trends of periodic table. Okay. Okay. Um, there we go. Okay, you can still see my screen, right?
Pardon? Yeah.
You can still see my screen. Okay. Chemical property. All right. Okay, so take a look at this. Chemical bond. Did you guys talk about bonds in under chemical properties?
Pardon?
Did you talk about bonds, chemical bonds?
I think so.
Okay. All right. So, um, okay. So I'll not go too far, but I'll just try my best to distinguish between ionic bonds and covalent bonds. Okay.
Okay.
Ionic bonds happen between two elements. One is usually a strong metal, and the other one is usually a strong non-metal. Let me say it again. Ionic bonds usually happen between two elements. One is usually a strong metal, and the second one is usually a strong non-metal. Now, what happens in that case? One will lose its electron, willingly lose its electron to the other one, so that the other one that is a strong non-metal will do what? Attract the electron from the other one, which is a strong metal. Please take note, non-metals are the ones that like to do what?
Yeah.
Attract. Yes, they attract electrons to themselves. Okay, did you get that?
Yeah. Wait. Is there anywhere? Because I don't have my notebook on me. I only
Okay,
have.
you want to do a screenshot?
Yeah.
Okay, all right. Okay, okay. Don't worry. So let me go to something that you would understand better. So some of these concepts are a bit okay. Okay, can you see this?
Mm.
Okay, good. So if you want to do a screenshot, you can do a screenshot of this. This is a very good example of what I was explaining. Very good example. Sodium chloride. Sodium is a very good metal, and chlorine is a very good non-metal. So have you been able to take a screenshot?
Yes.
Okay, good. So what would you say is the main thing about ionic bond? There is a complete transfer of what? Electrons. The sodium donates an electron. The chlorine collects that electron. Okay. And then of course, by the time you look at sodium, you will see that sodium's outermost shell does not have any electron anymore. It's now on what? Now on chlorine. Can you see that? It
Mm-hmm.
moved from sodium to chlorine. And chlorine, of course, guess what? Chlorine had 7 electrons. Look at the picture on the left versus the picture on the right. The picture on the left, let's count how many electrons are there in chlorine's outermost atom, outermost shell. 1. Are you with me?
Yeah.
Okay. So let's count 1, 2, 3,
Concentrate.
5, 6, 7. Okay. Now every element strives to have 8. That's the law. Okay. Every element strives to have 8. So chlorine would desire strongly to take the electron that sodium will gladly give away or gladly donate. And that's why you can now see on the right hand side, chlorine has 8 because it has taken that one electron from sodium. And take a look at sodium. Sodium too does not have, seems not to have an outermost electron anymore. But take a look at the shell that's inside sodium. Let's count how many we see there.
Small.
1, yes. Did you say something?
No.
Okay. 1, 2, 3, 4, 5, 6, 7, and 8. So that means both of them are stable now. Sodium has 8 in its outermost shell. Of course, when I say outermost shell, its former outermost shell now doesn't have any electron anymore. And then chlorine now has 8 electrons too in its outermost shell. Okay, so both of them would form a very stable compound known as sodium chloride, and that's stable salt. Okay, now the one I want to, okay, all right. So these are the key points. I've already explained it, but you can screenshot this too, just so that you remember. Are you done screenshotting? Once you're done, please let me know. We'll only talk about ionic and covalent bonding. Yes, and then we'll talk about more as based on what you do tomorrow.
Mm.
Have you taken a screenshot?
Yeah.
Okay. All right. So look at the key points. Loss or gain of valence electrons allows ions to obey the octet rule. The octet is 8. Okay, 8 in outermost shell, and that will make them to be more stable. Ionic compounds are typically neutral. So yeah, that's what we usually expect. All right, so look at covalent bonding. Now, the difference between ionic bonding and covalent bonding is this. In ionic bonding, there is a full transfer. It's like me saying, I gave you something. that's what I gave you is in your hands. It's no longer in my hands. That is a full transfer, ionic bonding. But when it comes to covalent bonding, it's like a sharing thing. That means I want you to think about two people holding one ball. One
Mm-hmm.
person is holding one part of the ball, and then you are holding the second part of the ball. So in other words, the ball is in between both of you. It's not fully on your side, and it's not fully on the person's side. That is covalent bonding. Okay. So think about covalent bonding like that. It's like a
Mm.
sharing kind of arrangement. Okay. It's not a full transfer from one to the other. Okay. So that's the difference between covalent bonding and ionic bonding. It's the sharing of electrons between what? Atoms. It kind of stays in the middle and makes those two atoms to be what? Stable. Okay. So how do elements that have covalent bonds usually occur? You would see that between elements, atoms of the same element, okay, and it's usually non-metals, usually. Um, and this bonding occurs primarily between non-metals. Okay, we've already said that. However, it can also be observed between non-metals and metals. Okay, so let's take a look at okay. I'm not sure. Okay, is it looking plain? This is an example of covalent bonding. Okay. All right. So this one, you can see how covalent bonding is represented. We just use dots for the electron. Those two dots in between are the dots. Let me annotate where the dots I'm talking about are. The dots here, um, the electron here, and the electron here. This one. Those two electrons will be shared between chlorine and phosphorus. And of course, you can also tell that, what do you call it? This electron and this one will be shared. Okay? Did you get that?
Mm-hmm.
Okay. So now, what is the aim of sharing, you know, electron? Same thing. There is always this desire for every element to have 8 electrons in its outermost shell. Okay, so did you get that?
Mm-hmm.
So always remember there's a rule called the octet rule, and that's what I just stated now. All right, so you can do a screenshot of this. Let me move on the slide for you. You can. Oh, all right, so that is some key points from. Okay, so do you have any questions?
No.
Okay, so like I said, I don't want to go through the but I'll just say that um And of course, some of these these two things that we discussed now influence the way some those compounds that they would form would behave. For instance, table salt. If you want to melt table salt, uh, it's going to be at a very high temperature. Okay, because it's solid and the bonds holding them together are very strong. In ionic bonds, very strong. Trust me, very, very strong. All right. So, um, so you might want to just answer these questions. Which bond is stronger? You can see that ionic bonds are stronger. Say because the uh, ionic bonds take up more energy to break down covalent bonds. Yes, that is a fact, and that is mostly because of the way ionic bonds are formed. Ionic bonds don't share. There's a transfer of electrons, while electrovalent while covalent bonds um, um, are not as strong as that as ionic bonds. Okay.
Okay.
Yes. All right. So please don't forget to get the you know screen either like I said screenshots of your notes or pictures of your notes. Clear pictures so that you will not start wondering what exactly um, you wrote. Yeah. Okay. So, are you good?
Yeah.
All right. So, I'll do. I'll expect that we would have something more to work with, so that we'll be able to review for your test better by tomorrow.
Mm.
Okay. So I think we can we can call it a day here. Um, okay. All right. So we meet at the same at 7. Sorry, 6 your time tomorrow, right?
Mm-hmm.
You see,
Okay.
why don't you ask
I
them to
hope
do
to.
Tuesday so that you are ready for the test for Wednesday because the test is on Wednesday.
Okay. Okay, wait, Uncle. I'd like to ask if you can do our lesson on Tuesday.
So that you can prepare for Wednesday.
On Tuesday.
Yeah.
And the
Hmm.
reason.
So I can prepare for Wednesday.
Oh, okay. Let me see. Oh, I have a couple of classes scheduled for Tuesday. Let me see what time. What time would I be doing? Okay. Um. So my Tuesday class would be off by let's say 7:30. Okay. Okay. So that would be 6:30 your time. Okay. All right. Okay. So do you think you can work with that? And you'll be ready by that. You'll be available by that time. 7:30, 6:30 your time.
Yes.
All right. Okay. I'll just see how I can. Oh, I hope I won't be too tired. But yeah. Okay. No problem. We'll do that. We'll do that 6:30 your time on Tuesday. So but then that means you really have to make sure you get those those pictures or screenshots by tomorrow, right?
Mm-hmm.
Okay. All right, that will be fine. Okay. All right. So enjoy the rest of your evening, and yeah, be good.
Okay. Bye, uncle.
All right. Goodbye.